Precision agriculture. 1.1 Definition. Precision farming is the technology which involves the targeting of inputs to arable crop production according to crop requirement on the localized basis. Stafford, 1996. Precision agriculture can be defined as the application of principles and technologies to manage spatial and temporal variability associated with all aspects of agricultural production for the purpose of improving crop performance and environmental quality. Pierce and Novak, 1999. Precision farming is generally defined as an information and technology-based farm management system to identify, analyze and manage variability within fields by doing all practices of crop production in right place at right time and in right way for optimum profitability, sustainability and protection of the land resource. Precision agriculture is a systems approach to farming for maximizing the effectiveness of crop inputs. 1.2 Objectives of precision farming. To develop a methodology for identifying the causes of within-field variation in crop performance. To develop practical guidelines required to implement precision farming technology to achieve best management. To explore the possibility of using remote sensing methods and GIS to enable management decisions to be made in real time during the growth of the crop. To determine the potential economic and environmental benefits of using precision farming technology in cropping system. 1.3 Need of precision farming to increase production efficiency, to improve product quality, use of chemicals more efficiently, energy conservation for. To increase input use efficiency, soil and groundwater protection, improve soil structure. 1.4 Components of precision farming information or database. Soil, soil texture, structure, physical condition, soil moisture. Soil nutrients, H. Crop, plant population. Crop tissue nutrient status, crop stress, weed patches, weed type and intensity. Insect or fungal infestation, species and intensity, crop yield. Harvest swath width, H. Climate, temperature, humidity, rainfall, solar radiation, wind velocity, H. In fields variability, spatially or temporally, in soil-related properties, crop. Characteristics, weed and insect pest population and harvest data are important databases that need to be developed to realize the potential of precision farming. Technology. Technologies include a vast array of tools of hardware, software and equipments. Global Positioning System, GPS, receivers. GPS provides continuous position information in real time, while in motion. Having precise location information at any time allows soil and crop measurements to be mapped. GPS receivers, either carried to the field or mounted on implements, allow users to return to specific locations to sample or treat those areas. Differential Global Positioning System, DGPS, a technique to improve GPS accuracy that uses pseudo-range errors measured at a known location to improve the measurements made by other GPS receivers within the same general geographic area. Geographic Information Systems, GIS. Geographic Information Systems, GIS, are computer hardware and software that use feature attributes and location data to produce maps. An important function of an agricultural GIS is to store layers of information, such as yields, soil 5. Survey maps, remotely sensed data, crop scouting reports and soil nutrient levels. Remote sensing. It is the collection of data from a distance. Data sensors can simply be handheld devices, mounted on aircraft or satellite-based. Remotely sensed data provide a tool for evaluating crop health. Plant stress related to moisture, nutrients, compaction, crop diseases and other plant health concerns are often easily detected in overhead images. Remote sensing can reveal in-season variability that affects crop yield, and can be timely enough to make management decisions that improve profitability for the current crop. Variable rate applicator. The variable rate applicator has three components: A. Control computer, B. Locator, and C. Actuator. The application map is loaded into a computer mounted on a variable rate applicator. The computer uses the application map and a GPS receiver to direct a product delivery controller that changes the amount and/or kind of product, according to the application map. Combine harvesters with yield monitors. Yield monitors continuously measure and record the flow of grain in the clean grain elevator of a combine. When linked with a GPS receiver, yield monitors can provide data necessary for yield maps. Management. Information management. The adoption of precision agriculture requires the joint development of management skills and pertinent information databases. A farmer must have clear idea of objectives of precision farming and crucial information necessary to make decisions effectively. Effective information management requires many more than just keeping analysis 6. Tools. It requires an entrepreneurial attitude toward education and experimentation. Decision Support System (DSS), combination of information and technology into a comprehensive and operational system gives farmers a decision to treat the field. For this purpose, DSS can be developed, utilizing GIS, agronomic, economic and environmental software, to help farmers manage their fields. Identifying a precision agriculture service provider. It is also advisable for farmers to consider the availability of custom services when making decisions about adopting precise, site-specific crop management. Purchasing the equipments and learning the necessary skills for precision farming is a significant upfront cost that cannot be affordable for many farmers. 1.5 Steps in Precision Farming: Identification and Assessment of Variability. Grid soil sampling. Grid soil sampling uses the same principles of soil sampling but increases the intensity of sampling compared to the traditional sampling. Soil samples collected in a systematic grid also have location information that allows the data to be mapped. The goal of grid soil sampling is to generate a map of nutrient, water requirement, called an application map. Crop scouting. In-season observations of crop conditions like weed patches, weed type and intensity. Insect or fungal infestation, species and intensity. Crop tissue nutrient status. Also can be helpful later when explaining variations in yield maps. Use of precision technologies for assessing variability. Faster and in real-time assessment of variability is possible only through advanced tools of precision agriculture. SAT. Management of variability. Variable rate application. Grid soil samples are analyzed in the laboratory, and an interpretation of crop input, nutrient, water needs is made for each soil sample. Then the input application map is plotted using the entire set of soil samples. The input application map is loaded into a computer mounted on a variable rate input applicator. The computer uses the input application map and a GPS receiver to direct a product delivery controller that changes the amount and/or kind of input, fertilizer, water, according to the application map. Yield monitoring and mapping. Yield measurements are essential for making sound management decisions. However, soil, landscape and other environmental factors should also be weighed when interpreting a yield map. Used properly, yield information provides important feedback in determining the effects of managed inputs such as fertilizer amendments, seed, pesticide and cultural practices including tillage and irrigation. Since yield measurements from a single year may be heavily influenced by weather, it is always advisable to examine yield data of several years including data from extreme weather years that helps in pinpointing whether the observed yields are due to management or climate-induced. Quantifying on-farm variability. Every farm presents a unique management puzzle. Not all the tools described above will help determine the causes of variability in a field, and it would be cost prohibitive to implement all of them immediately. An incremental approach is a wiser strategy, using one or two of the tools at a time and carefully evaluating the results and then proceeding further. Flexibility. All farms can be managed precisely. Small-scale farmers often have highly detailed knowledge of their lands based on personal observation and could already be modifying their management accordingly. Appropriate technologies here might take this task easier or more efficient. Larger farmers may find the more advanced technologies necessary to collect and properly analyze data for better management decisions. Evaluation of precision farming. Economic analysis, whether it is cost-effective. Environmental assessment, does it improve the quality of environment or at least not harm? Rate of transfer of technology, do farmers adopt it rapidly? 1.6 Scope of precision farming in India. The concept of precision farming is not new for India. Farmers try their best to do the things for getting maximum possible yield with information and technologies available to them, but unless or until total information about his field and advanced technologies are available, they cannot do precision farming in perfect sense. In India, major problem is the small field size. More than 58% of operational holdings in the country have size less than 1 hectare. Only in the states of Punjab, Rajasthan, Haryana and Gujarat more than 20% of agricultural lands have operational holding size of more than 4 hectare. When contiguous fields with the same crop are considered, it is possible to obtain fields of over 15 hectares extent in which similar crop management are followed. Such fields can be considered for the purpose of initiating the implementation of precision farming. Similar implementation can also be carried out on the state farms. There is a scope of implementing precision agriculture for crops like rice and wheat, especially in the states of Punjab and Haryana. Commercial as well as horticultural crops also show a wider scope for precision agriculture in the cooperative farms. Nearly 2/3 arable land in India is rain-fed. The crop yields are very low, 1/1, and very good potential exists for increasing productivity of rain-fed cropping systems. 1.7 Advantages of precision farming. Overall yield increased 9. Efficiency improvement, reduced production costs, better decision making in agricultural management, reduced environmental impact, accumulation of farmers' knowledge for better management with time. 1.8 Drawbacks of precision farming: high costs, lack of technical expertise, knowledge and technology not applicable or difficult, costly for small land holdings, heterogeneity of cropping systems and market imperfections. 10.